So I'm going to do a little bit of lecture here at the beginning of class because the exam is brief. So we'll get started on the next subject. I want to talk about a couple of things relating to the experiments. Are there any questions before I get started? Questions? Place this over here. Why is that? Something about that side of the world. You can see outside. Yeah, that's nice. The weather's nice. So.
This is slightly not hot.
Yeah, slightly not hot.
Yeah.
Still very humid.
It's very humid.
I went walking this morning and it was like wet. Those temperatures. It's supposed to be like 60 degrees, like Friday morning.
Really?
Yeah, isn't that nice? That'd be really nice.
I'm gonna cry tears of joy.
Pardon?
Tears of joy.
Yeah.
We're talking about Fahrenheit.
Yeah, Fahrenheit.
It's not gonna be 6 degrees.
No.
That's not helping the.
Did you watch the superfluid helium videos? That was pretty neat. Yeah.
I have a question about that. So, like, doesn't that go against the principle of non-contradiction?
How so?
Because something is viscous and non-viscous at the same time.
Well, it's not a single substance, so it's in this case it's a mixture of two fluids, right? Yeah. Just like you could put oil and water together, it's really just two different substances mixed together, not a single substance.
Yeah. Well, the superconductivity with that's like no resistance, right?
Yes.
How?
No electrical resistance.
Yeah. No electrical. Or that's is there other resistances?
Sure. There's like resistance to fluid flow. Viscosity is a resistance.
Okay. Sorry. Oh,
And there's thermal resistance to heat flow.
so it's all like correlated with the electron with the charge flow.
In the case of superconductivity, it's no electrical resistance, no resistance to flow of current.
Okay, great. But there's still like is some type of resistance being okay, great. I was just curious about that.
It can be correlated with other things like thermal resistance. Superconductivity specifically refers to no resistance to electrical current. Yes, ma'am.
Can you talk about how, like, why the heat spreads in waveform and like second sound?
Yeah, I think we'll have to wait on that. It is a quantum effect because heat normally diffuses, right? Heat flows more like a random walk, or similar to that. If you were to take a dye in a fluid and put a drop, then wait, and you'll see the dye diffusing outward. That's more like what heat flow is normally like that. And the second sound is not like that at all. It's some kind of wave. What kind of wave is it? It's not an electromagnetic wave. It's not electromagnetic wave. What is it a property of? In this case, second sound. Second sound. It's in the video that you were supposed to watch. Yes, sir.
Is it quantum in the fluid?
No. The fluid is the substance. The fluid is the substance. So it's a wave in the liquid helium, superfluid helium. So it's got something to do with the motion of the parts of the superfluid. So it's a really good question. What is that all about? And why is that acting differently below the lambda below the temperature? So if we're going to have to put that one on hold, that's one of the ones we would like to understand. In fact, we can kind of, that involves the first stage of doing the quantum mechanics for us is to do one electron in one hydrogen atom. Superfluid involves the cooperative motion of parts. So now we have to have more than one particle. So we're going to have to continue the development of quantum mechanics to dealing with multiple particles, multiple electrons, for example. add multiple particles. And we're not going to have time to get to that stage. It's in the book. It's a later chapter about how to deal with quantum systems with multiple particles. So we're going to treat the electron as moving around the proton. We're going to treat the proton as just a fixed thing. And the electron, we're going to study the motion of the electron around the proton. We're going to study that a lot. But then to really understand superfluid flow, you have to do the quantum mechanics of multiple particles. And so it's very interesting subject. So I'm just giving you a flavor of all the interesting things that have been discovered since 120 years ago. A lot of interesting stuff. In fact, somebody suggested the following idea. If we have a second sound as a wave, then how about diffracting it? So let's go back to that setup. And that's described in the video. There's a heater, it's immersed in a cell of liquid superfluid helium, and then a detector that detects the heat. How would we turn this into a diffraction experiment? We have a wave, which is the second sound. It's not diffusive. It's called ballistic. It's just a wave propagating through. How would we turn this into a diffraction experiment? Thoughts? Yeah,
Put a double slit in there, or
put a slit. Put some kind of barrier so that the wave is coming up to a barrier with a slit. And then we would, to really do it interesting, we'd want to move the detector around in different positions beyond the slit. So the wave comes up, diffracts through the slit. We want to move the detector around so we could detect, hopefully, the interference pattern that we would get maximum and minimum heat flow. I don't know if anybody's done that. I'm really curious. It might be interesting to give that a try. Maybe just look, see if somebody's done that. Yes, ma'am.
Would the interaction with the double slit material change, like, would it not reduce the heat more than just a fraction?
Well, that's a good question. That's a good question. So obviously the barrier has to be itself at very low temperature. So it has to come into equilibrium with the fluid. So, but the question I don't think, and so some of that is actually, so where there's viscosity, that part of the fluid which is viscous is going to flow differently through the slit. So it's an interesting question. Think about how that might all work out. I don't know if it's been done. I thought it was an interesting idea. Somebody said, can you do that? Okay, now I did want to clarify something. I think there was some confusion. When I did the laser experiment with the diffraction slit, right? Just a single slit. It's formed by having a slit through a piece of metal that's put into the laser beam. And the slit is really quite narrow, but you can almost see it. And then I was changing that width, the opening. That's what was changing, not the distance between the laser and the barrier. Okay, so this distance to the laser and the distance to the screen, that was all unchanging. What I was changing was the slit width. And then when I went to two slits, the double slit, I changed this. I had two slits, so there's a barrier here and here. And I'm keeping the slits the same width, but changing the separation. So everything is happening this way. I know you couldn't see it very well, unless you came down and looked at it. Everything is happening in this dimension, not this way. So I think there was some confusion about that. Also, because of me, I did cause some confusion, so I want to just clarify this with regards to the text. Of course, in the background, when we're investigating the understanding of these experiments, they cannot contradict the basic principles of physics. These are things that are generally true for all physical things. And so we have to keep that in the back of our minds. These basic principles that we learn, things exist, things change, principle of non-contradiction, principle of causality, substance and properties, this doesn't change. These things are not waiting for more experiments. They're things that we know to be true. So it doesn't make any sense to say that a particle, by which we mean something which is confined to a small volume, that a particle could go through two slits at the same time. That makes no sense. Even though you will hear that and you will read that in some quantum textbooks and people talking about it, it just doesn't, it's not logical. And in fact, it is not a conclusion. And we will, what we showed instead was that you're forced to think that there are two entities, a particle and a wave, guiding wave. These are acting together in the double slit experiment, or even in single slit diffraction. Okay. All right, so that's one thing to be clear about. But then the second thing, there are three more specific things to remember, and this is what's in the textbook, and I added one, and somebody noted, you've got four things, and then list three. Okay, so I'm trying to clear up the confusion. It's correct in the textbook. Now this is in agreement with the textbook. There are three more specific things that we're understanding from the experiments. So the idea here is that we're going from general to specific. So the general principles we talked about, and now we're adding more concrete information from observations about nature. And this is the way to go. You go up and down from abstract to concrete, general to specific. So we understand things generally, we add some more specific information, but that we have to understand in relation to the general. And so we keep going up and down this ladder, and he talks about this in the textbook, about how this process goes. Okay, so the things that three specific things that we learned from the experiments. The first one is that the particle is accompanied by a guiding wave. It's not just one entity, but two. And the second is that the guiding wave structure, being wave-like, can set up interference and resonant structures, leading to quantization. And we'll see how this works, for example, in the hydrogen atom, and also in the double slit. We'll go back to examine those experiments in detail once we have a more robust empiriometric theory in place. Once we have something to work with, more robust. Okay, and also an important thing, the third thing is that quantum mechanics does not deal with single systems, but deals with ensembles of systems. And now, if you're going to do an experiment, for example, the electron going through the double slit, you actually make 1 million copies of this thing and let each electron go through, and you're collecting what the ensemble does. Or like in the case of the random walk, we're not interested in what one random walker does. We're not interested, he has one guy starts here and he's got 100 coins, and he flips one, he goes to the right, and his heads to the left, and so he ends up over here. Okay, we're not interested in just one. We want to have 1 million people doing this. Each one has 100 coins. And then we collect the distribution, the probability distribution, meaning how many end up actually back at the same place, and how many end up a net of one step to the right, how many end up at a net of one step to the left, and so forth. Okay? So the ensemble is key to understanding quantum mechanics. And it's a very common mistake to think that quantum mechanics is giving you information, detailed information about individual systems. It's not. It's always giving predictions about ensemble measurements. And that's key. Yes, sir.
Oh, sorry.
Oh, okay. All right. Okay, so this I inserted this on the list because it's important. And then I messed up what was in the textbook. So anyway, just wanted to clarify. So everybody okay with these things? These two basic sets? Okay. Okay, so let's see. We're going on now to let's see. We're going on now, moving on to, oh, I don't need this. I'm going to turn this off. We're going on now to the study, inserting a chapter between the first and the second. Because the second chapter assumes a little bit of math that I can't assume that you have. I think you'll find this very interesting. Even if you've had it before this subject, you're going to study complex numbers and complex mathematics. Even if you've had it before, I think you'll learn something from this. In fact, I'm sure you'll learn something from this. So one of the things you're going to read in relation to this subject. So we have chapter M. Chapter M is this digression into complex analysis, complex variables, complex numbers. Beautiful subject in mathematics. I highly recommend that to you. Wonderful subject, just really elegant. So beautiful stuff, and it's used a lot in physics. Really, again, like a lot of parts of mathematics, it comes out of physics in a very natural way. And you'll see how it works here. So it's used by engineers a lot. It's used anytime there's a kind of oscillatory wave-like motion. Complex numbers are a very compact way of describing and dealing with wave-like behavior. Yes, sir.
Actually, that reminds me, you asked me to ask you about the why, but or some of your things have to be periodic.
Oh, right. Okay. Yeah, the question at the end of class, I asked him to ask again today because it was a good question. Why is it that there had to be, why does the wave have to be resonating? Why does, if we're talking about a wave going around a circle, then why does it have to be coming out to be, and the wavelength has to be an integer fraction of the circumference? The reason for that is you want to resonate the structure. The idea is that something is going on with the quantization of the electrons and the hydrogen atom. And the guys who were working on in the early days of quantum mechanics recognized that if there was a wave structure, then there could be, this quantization could be due to a kind of resonating condition. So you can imagine swirling a glass with water in it, and you get the wave traveling around like this. Suppose you want the condition where the wave is constructively interfering with itself as it goes all the way around, and it ends up at the same point with another maximum in the wave. So you have a standing wave now, or a traveling wave, but you want it such that it's constructively interfering with itself and not destructively interfering with itself, which would require that the number of wavelengths has to match up to be an integer, so it's coming back in phase with itself on the opposite side. And that's the idea behind this Bohr-Sommerfeld quantization condition. It's, you know, it's got aspects that seem to be correct, but the basic idea that it leads us to is that the quantization can come from this kind of structure, this resonating structure of something, a guiding wave. So we'll see how this works when we get to the hydrogen atom and we start having a more defined, robust mathematical expression, namely the Schrodinger equation. We'll begin to understand more about what that is like. Okay, good thing. All right, so let's take a step over to algebra. And you've all learned this expression of the solution, that there are two roots of this equation, two solutions for this. And this is given in the form of the quadratic equation. When you learn this in class, by the way, in school, that puts you into maybe 1/10% of the world's population knows this. I mean, it makes it some really tiny fraction. It's amazing because it's really pretty elementary. Mathematics, that algebra that was developed by Descartes around 1600. But you're in a tiny fraction of the population. A lot of people don't know this. Okay, and we said that, and of course you learn that this is related to where a parabola will intersect the axis. So we plot this function, ax squared plus bx plus c, we get a parabola as a function of x. And where that parabola crosses the x-axis, that will be the solution to this equation. And so we see that the one I've drawn there doesn't cross, so there are no solutions. Whereas a normal situation would be parabola goes like this, or parabola goes like that. So in the case where it doesn't cross, we say that there are no real solutions. I qualified it right there. There's just no solutions for numbers, for ordinary numbers x. But it's as if somehow the arithmetic, the algebra has just given up at that point. So complex numbers were motivated by an understanding of solutions of polynomial equations like this cubic quartic equation. How to solve these equations, and can we somehow generalize the solutions that we get when there is a crossing to something that would be like solutions to this equation where it doesn't actually intersect? So that there would always be two solutions to this equation, but not corresponding to numbers along a line, normal x-axis. Well, that would happen here. If you look at the key here is called the discriminant, staying under the square root. If this is positive, then you're taking the square root of a positive, and that gives you two zeros. If this discriminant is equal to 0, then you're talking about a case where the parabola just kisses at one point. There's one solution. If the discriminant is negative, that corresponds to this situation. And of course, the problem here with ordinary mathematics is we have the square root of the negative number, which doesn't exist. So that presents a kind of challenge to Descartes and others. How do we deal with this more general situation where we could have corresponding solutions to this equation even where this is negative? And that's kind of where this thing was motivated, was by looking at solutions to these polynomials. Okay, so you're going to read a paper, an article by Dr. Rizzi. It's on the canvas. It's a really beautiful article, by the way. It really helps to illuminate what is the subject of mathematics. It goes back to the statement that we've discussed earlier, that math is the study of quantity, which is the base property of physical things, having parts and shape, which is a slice of quality associated with quantity because it's the bound to extension. So he brings that at the beginning, and then he shows how we get the axioms of the mathematics that you learn: addition, subtraction, multiplication, real numbers, including both rational and irrational numbers. What does all that mean? What's an irrational number? Understood, starting from this basic physics of just understanding length, extension, having parts. So it's a beautiful article. And if you would like, you can, well, I'm assigning the appendix for you to read on complex numbers. Complex numbers and complex mathematics. So this is assigned. If you're interested in doing some extra credit, and if you're up to date with the homework, I don't want this in place of catching up with homework. Most of you aren't behind. So you can read more about this article. Start at the beginning and read through it and write up something and turn it in. I'll give you extra credit because it's a beautiful article. But it takes us a little bit off course here for this purposes of our course. Yes, ma'am.
Something is in like a summary, the key points.
Yeah. Yeah. Maybe set a goal for yourself to understand what an irrational number is. That's really interesting. Square root of 2. It's irrational. What's that mean? You might think about it in terms of the repeating of the digits, but there's something more profound about an irrational number than that. Okay, but you'll read about complex numbers. And so I don't want to take up much more time here, except to say he first describes in this article about just the number axis, and we can think of this in very simple terms as being something relating to a displacement. So I move some distance in some direction to this side, or I move some distance to that side. And that corresponds in this to having an origin. And then it's interesting how this works, because we start using positive and negative numbers. But I'm always moving a positive distance, right? I move this way, how far did I move? I moved a foot or a yard. How far did I move? Just in a different direction. So what we do is combine positive and negative numbers, use them in such a way as to give us direction. So positive means to the right, negative means to the left. A displacement to the right followed by the same displacement to the left, different opposite direction, cancels out and come back to the origin. Very interesting. It makes it very convenient because you don't have to talk about left and right motion. Just talk, motion to the left is negative motion to the right. What interesting. Why would you want to do that? It's much more compact just to talk about that kind of displacement. A negative displacement is just motion to the left. And we don't have to worry about whether we're talking about right or left. It's very compact. Okay, so now he's going to extend this. We need more than one dimension. So he's going to extend this. And you have learned how to use vectors. There's, in the history of this subject, though, extra dimensions were brought in a different way. There's vectors are the ones you normally learn for the x hat, y hat, z hat. Were developed by Gibbs, and that's commonly what we use today. That wasn't the only choice for mathematics to describe multiple dimensions. Complex variables and quaternions were also used and are interesting and very useful, but not for the original way that they were intended. So very few people use quaternions to describe motion in 3 dimensions anymore. We use vectors. But quaternions is a very interesting subject in mathematics by itself. Complex numbers also a very rich subject in mathematics, but not usually used to describe 2-dimensional motion in a plane. So that's where it started off, was describing motion in 2 dimensions or objects in 2 dimensions. Okay, so I have get out some blank paper, and I'll give you until I'll give you 25 minutes. Probably don't need that much time. And on your way out, please collect from me your test from last year. Appeared on campus, trade for this or on campus.